Oops, I did that last time. Hey, so we're going to take a quick look at hydrates, okay? Hydrate is an ionic compound that has molecules of water attached to the ionic formula units, okay? I'm going to explain that a little bit more on my board. So hydrate is an ionic compound that's got molecules of water attached to it. It is still solid, it's shiny, it's crystal-like. You will see the names. I'm just going to give you some examples. We're talking about hydrates here, all right? We are talking about hydrates. Oops, there we go. Get a new marker. I'm starting to lose my markers. Some example would be copper 2 sulfate pentahydrate, right? Pentahydrate, iron 3 chloride hexahydrate. So if you recall the prefixes from covalent compounds, mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, that's where I'm getting these from. Copper 2 sulfate has a formula, right? Copper 2 sulfate. Now pentahydrate, okay? Iron 3 chloride hexahydrate. All right, iron 3 chloride hexahydrate. You can imagine a monohydrate, dihydrate, trihydrate, tetrahydrate, etc. Okay? Now I want you to realize that what this means here in this formula is that every 1 formula unit of copper 2 sulfate has in it 5 molecules of water. Or every 1 mole of copper 2 sulfate has in it 5 moles of water. Every 1 formula unit of iron 3 chloride has in it 6 molecules of water. Every 1 mole of iron 3 chloride has in it 6 moles of water. All right. Another thing to realize is that when it comes to these hydrates, these are common questions I receive. If you are asked for the molar mass of a hydrate, yes, you include the water. Yes, you include the water. So if I needed the molar mass of this compound, I would have to get the copper. Let me write this real quick. Includes water, right? I would have to get the copper, the sulfur, these 4 oxygens. I would get these 10 hydrogens and then another 5 oxygens, okay? All right. Now, another thing to realize is that the percent H2O in this hydrate, right, is simply equal to the mass of the 5 waters divided by the mass of the compounds, right? And then because it says percent, we would multiply times 100. All right, so let's go ahead and do that, and then we'll have those numbers and we'll use those numbers again in a moment. So the percent water is equal to 5 times 18.02. That's the mass of my 5 waters, 90.1 grams of water, divided by the mass of my copper 2 sulfate, which will be my 5 waters, plus my copper, 63.55, plus my sulfur, 32.06, plus my 4 oxygens, 16 times 4, and that is 249.71, and that is the molar mass of the CuSO4.5H2O, okay? To get the percentage, I just take 90.1 and divide it by the 249.71, and I multiply it by 100, and I have a compound that is 36.1% water by mass, okay? Now, I'm gonna get rid of this. I'm gonna keep that here. I'm gonna get rid of this. Guys, if I had a bigger board, if I could move this, I would work down. So I don't want you to work up in your notes. I want you to continue working down. Actually, I'm just gonna rewrite this because I want it to read from top to bottom. It's just, I want y'all to have good skills. I want your work to be nice. Okay, imagine a question that said, you have a 5-gram sample, right? This is what you have. You have a 5-gram sample of CuSO4 pentahydrate. And the question is, how many grams of it is water? Well, we know we could get 36.1%, or couldn't we say that there are 90.1 grams and 249.71 grams, and set that equal to how many grams of water would be in 5 grams of the compound, right? Either way, if you didn't already have that percentage, you know, it's kind of easier. But if you don't like math, right, we're just going to cross multiply here, cross multiply. And 90.1 times 5 equals, divided by 249.71 equals, and I see that I would have 1.8 grams of water in this sample. Okay, so you could use a ratio there. Another thing to know is what to do with a data chart. If you're given a data chart and need to solve a problem. So I want you to realize that we would take this hydrate, okay? And upon heating this hydrate, we would end up with the anhydrate. That is our compound without the water, and the water would be removed as a gas. This would be a shiny crystal-like solid. This would be a dull, chalky-like material. The gas is going to exit the system. Make sure you realize that we have a law of conservation of mass here, right? Very, very simple idea. And let's say that we are in the lab, and in our lab, we get the mass of our empty crucible, right? A crucible is a small container. You can heat things to very high temperatures. And we get our crucible and we get its mass, and we find it to be 21.30. We then put our sample of our hydrate. We'll figure out what type it is in a minute. We put that sample of our hydrate in our crucible. We remass it, and we get 31.35 grams this time. Notice it went up because we put our hydrate in there. We then take that crucible, all right, with our hydrate in it. We put it on our ring, which is attached to our ring stand, which has a Bunsen burner. Of course, well, that's how it would be in our lab. And we heat it. And we heat it, and then we take it off and we mass it, right? Once we think it might be done. How do we know? Because we get this dry, chalky-like substance. We heat it several times. We heat it and mass it. Heat it, let it cool, get the mass. Heat it, let it cool, get the mass. Heat it, let it cool, get the mass. We do that however many times we need until those mass values stop changing. Because at that point, we can conclude that the water must be gone, that all of the water has been removed from the hydrate. Once the mass stops changing, all of the water has been removed. So what we see that is after all these attempts, the mass of the hydrate, oops, sorry, this is going to be the mass of the crucible. Mass crucible after last heating, right, is found to be 29.87 grams. Okay, and the question is, what is the formula of this hydrate? Okay, a barium chloride. Okay, this is a barium chloride hydrate. So what is the formula and name of this barium chloride hydrate? Okay, and we have some mass data here. That's a question. Okay, well, we know that it's barium chloride. We know it's dot some number H2O. And that number reflects the ratio of moles of water to the moles of the anhydrate. And in this case, that anhydrate is barium chloride. So if I can get these two numbers and divide these two numbers, I have my answer. So how many moles of water were in this hydrate? Well, I don't know, but I can easily figure it out because I know that the hydrate minus the anhydrate equals the water, right? If hydrate equals anhydrate in terms of mass plus water, then doesn't the water equal the hydrate minus the anhydrate, right? Very simple, very simple. This is with the water, this is without the water, the difference is the water. So let's look at our data chart here, okay? What we see is, I've got my crucible, okay? Crucible and the hydrate, okay. So the mass of my hydrate will be equal to the mass of my crucible and the hydrate minus my crucible, which by itself is 21.30. So if I subtract that, 50.10, that would be the grams of my hydrate. All right. Let me check that to make sure I'm not doing anything stupid, because I really don't want to have to make this video again. Okay, great. And then the mass of the water, right, is equal to the mass of the hydrate. I already wrote that there. So this is my hydrate. This is why things are good to be labeled. 10.05 grams of hydrate. The barium chloride, you could write that if you wanted, minus our anhydrate. Oh, we don't need to get that. Okay, mass anhydrate. Well, where was the anhydrate after heating it? The anhydrate was sitting in the crucible. So if I get the mass of the crucible after the last heating, it has its anhydrate in it. So if I take the crucible, and if I take the mass of the crucible and the anhydrate and subtract from it the mass of the crucible, I'll be left with the mass of my anhydrate. So the mass of the anhydrate is equal to the 29.87 grams. That's the crucible with the anhydrate minus the crucible, right? And that gives me 8.57 grams of anhydrate. Okay, but what I need is the mass of the water. So if I take my hydrate and subtract my anhydrate, I have my water. So here's my hydrate. This is my compound with the water. Here's my anhydrate. Notice I've got everything labeled so I can find my numbers. They're not just floating around. And you see where my numbers are coming from. Okay. Nice and labeled, nice and labeled, nice and labeled. What do I get there? 10.05 minus 8.57. I should have done that in my head. I get 1.48 grams, and the hydrate minus the anhydrate is water. So, in order to solve a hydrate problem, I need moles of water. Well, I need to turn my grams of water into moles of water, and I'll do that by dividing by the molar mass. Okay. 1.48 divided by 18.02 equals 0.08213 moles of H2O. Notice it's labeled. Okay, so I've got that. Let's get the moles of our anhydrate. Oh, there's our mass of our anhydrate. It's nice and labeled. 8.57 grams. Remember we said it's a barium chloride. All right. We're going to need to get the molar mass of barium chloride so we can get our moles of barium chloride. So here we've got our periodic table. We know chlorine because we use him a lot. 35.45 times 2. And then barium, we'll find right here, it's going to be plus 137.33, which gives us a molar mass of 208.23. Okay, now let's take our 8.57 grams and divide it by our 208.23, and we'll see that we have 0.04116 moles of barium chloride. I'm not worried about significant figures because I need to get a whole number. Now I could do this here. Oh my goodness, so sorry, so sorry. Okay, so I now have my moles of my anhydrate, right? Moles of water, moles of anhydrate. If I divide those, right? If I divide those, you can easily see it's going to be a 2. 0.08213 divided by 0.04116. That's moles of water. Now, I've done more than necessary here, but just realizing how hard it is to teach this way. But you can see that's going to be a 2. 0.08213 divided by 0.04116 equals 1.995. That is a 2. Okay, I've got my work shown. It's labeled. If I could work further down the paper, I would do that. Instead of working over, I would work down. Okay, and not be concerned with how much paper it takes. I know that sounds bad. Our answer was 2. And that means our formula is BaCl2.2H2O. And that is barium chloride. Does not need to be capitalized. I do that inconsistently. Dihydrate. Okay. Now, let's talk about something. Error analysis. What if my answer was too big? What might I have done wrong? I cannot say I heated it, I measured wrong. The numbers were wrong. I can't say that. Okay, what did I do? Did I heat it too long? Did I heat it not long enough? Well, this number was too big. That number came from here. right? So if this number was too big, that means either this was too big or this was too small, right? Well, if I overheated it, then it would appear as though I had more water than I did. Maybe this substance started to decompose, right? So if it was too big, it could be due to overheating it, because overheating it could cause the mass of the anhydrate to decrease. It could cause it to start decomposing, which would cause the mass of the anhydrate to decrease, which would make it appear as though I had more water, which would make this number larger. You have got to be able to make these claims and to support them. If this number had been too small, then we would see that the water amount was either too small and or the barium chloride amount was too big. In either case, that could be attributed to us not heating this enough, because we did not get all the water out. Therefore, it appeared as though there was less water than there was, and it appeared as though there was more anhydrate than there was, because some of the anhydrate was still hydrated. And when we divided this, we would get a value that was too small. And we did it. That is your hydrates. Rewatch the video, come up with any questions you may have, understand it. Okay, it's really easy. I kind of made it look hard, but that's because I'm trying to teach you on this whiteboard through the computer and stuff. It's hard. Bye. Over here. Bye.